Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and in this video I'm going to talk to you once again about exactly what is a number, yet another perspective, and hopefully this will appeal to those who up to this point still have questions about what it means to be a number. So let's begin. Now, first of all, you'll be able to find this article on academia, and I would suggest that you download that article and also study the link in the article, which explains the history of arithmetic. So I'll put that in the details section, but without further ado, let's see basically what is a number. So a number is a name given to a measure of a magnitude or size. Now this magnitude or size is typically what appears before a colon and is measured by what appears after it. Okay, so what you have here is you have a and it graduates number if you're able to measure using this part or equal parts of it. Okay, so that's all you really need to do. And let's exit the drawing. And so basically, what is a magnitude that is being referred to in the above definition? Well, given any line segment, like let's say this red one, we can only refer to it or differentiate it from other lines by comparing it to a known line segment like this green one, right? And of course, if there are any others, and we want to make sense of them, then both of them must have a common measure, this green line. That's what that means. So, given any ratio of magnitudes whatsoever, we can assign a name using a ratio of the natural numbers, which is just simply a ratio where what appears before the colon is a multiple of the chosen unit, and what appears after the colon is the chosen unit. All right, so let's see how this game works from beginning to end. So step one, we choose a unit magnitude of any size, and I've just chosen this random size. So this is the unit ratio, not the number one as you see over here, but rather the ratio of the unit, okay? And so step two, we assign names to all the multiples of the unit. So this is the unit itself, which is basically a multiple of itself. This here is a multiple of the unit, of this unit, and it's also known as the number 2, right? And this is known as number 3, and this is known as number 4. So the above are all fractions of ratios, all of these. That is 1, 1, 2, 1, 3, 1, 4, 1, etc. Now, since only the antecedent changes, these parts are the antecedent part of the ratio, we can simplify the above scheme to simply this, right? Where we just have one ratio, and we know that the green line is the unit. And then given, of course, that all the above ratios have quotientness, which means they all have a common divisor between the aliquot parts. So the common divisor in this case is this, and again in this case, and again this case, and this case. So we can denote their measure as a number using this notation. So this ratio becomes a number 1 by writing it like this, right? This ratio becomes a number 2, number 3, number 4. Now, of course, we could have written all these, and we do write these in algebra as 1 over 1, 2 over 1, etc., or just simply 1, 2, 3, 4, because we know that we are dealing with fractions whose denominator is the chosen abstract unit, okay? So now we can measure any ratio that has quotientness using these numbers. That is a ratio of numbers which we call a fraction. And step 3, since we don't care about the unit size, all that is left to do is to find the measure of a ratio's aliquot parts in terms of numbers, and then write this as a fraction to denote the completed measure. So now, not all ratios have a measure. So here are a couple of well-known examples. Do you recognize these? Well, if you said a constant pi and the constant root of 2, you'd be correct. Neither of those are numbers, because any attempt at measuring the above ratios results in the realizations of the constants pi and 2. And the constant does not mean it's a number. It means that anytime you try to measure it, you'll get the same result, the same approximate rational number, which is not the number itself, but only a partial measure. So it is incorrect to write pi is equal to circle periphery over circle diameter, because in order to be a fraction, both of these must be measurable in terms of the abstract unit. And of course the same applies to square root 2 or any other magnitude that has no measure. So once we write p over q, it is understood that both p and q have quotientness. In Greek, pilikotita. That means a common divisor. Now you'll find that word pilikotita in definition 3 of book 5, and most, in fact I've never met one modern Greek mathematics professor or teacher who actually understood the definition, and they don't use it. So the arithmetic of fractions in algebra is based on the exact properties of the arithmetic of fractions in geometry, with one exception. The unit is abstract and its size is relevant. So in using the abstract unit, we assume that when it measures another fraction or a number, because all numbers are fractions, that it can be divided into any number of n equal parts. So for example, to measure this particular line segment using this unit, we have to divide the unit, this unit, into 4 equal parts, right? And now we have established quotientness between this magnitude and the unit. And we have this ratio of this magnitude to the unit. But another way of doing this without any division is to simply extend the unit, this unit, by 3 times its length, as you see in this line here, where I'm pointing. And of course, you do the same with the magnitude being measured, this magnitude being measured. So extended by 3 times, okay? Or actually just taking 1, 2, 3, right? So in the above example, we deal with a number that is less than 1, that is 9/12 or 3/4. And if, however, the fraction or number is greater than 1, then it may be the case that we can apply long division to simplify the fraction. This process is called Obelisk Division. So I just want to see, have I done this right? I've said 3/4 and then I multiplied it by 3. Yes, that's correct. Okay, so this process is called Obelisk Division. So for example, suppose we have this ratio here that you see in front of you, with this antecedent and this consequent unit. Then the above unit, this unit here, measures the antecedent 3 times, right? Hence the number 6/2 or 3/1. And such division is defined only for fractions where the numerator is greater, such as 6/2 or 3/1. And we can do it this way to see that that measure is true. So if we wanted to measure 6 with 2, we subtracted 3 times, and that's the result, right? Now, in the case where the numerator is not an exact multiple of the unit, there's usually a remainder. And so here's an example, 9/4. If we want to measure 9 using 4, we need 2 4s and then 1 of 4 equal parts of 4, right? Does that make sense? So the unit is the remainder in this case. And in another example, 10/4, we have a remainder of 2 units, because 10 minus 4 minus 4 minus 2 is 0. And if you're wondering what exactly this approach means, then know that all that is happening here is that 10 is measured by 4 or equal parts of 4. That is, we need 2 4s and 1/2 of 4 to complete the measure of 10, right? Thus we could write 10/4 or 2 plus a half. Now, to learn much more than I've just explained to you, go to this link and read it. It's free. You can get it on Academia, and it will give you all the tiny details as these things are derived from the geometry. In other words, the geometry of similar triangles and all the propositions in Book 5. So that's pretty much it for now. If you haven't already become a subscriber, subscribe to my channel and spread the news. Tell your friends about it. Tell your teachers about it. Tell as many people as you can. And you can also contribute dollars or credits on my Odyssey channel, to which I'll place a link. And I hope, once again in the near future, to be making some more things clearer or revealing new knowledge to you that I haven't shared before ever on YouTube or anywhere else. So I'm still thinking about that. My name is John Gabriel, and this is a New Calculus channel. Till next time, goodbye.